this is where the magic happens. I'm no magician, so I hope you enjoy this. We have brought this presentation with the purpose of inviting a new way of thinking about distribution of biomass and grades. The typical pneumatic distributors that have been used for many, many years have some limitations, and we think that we're inviting you to explore a new way of doing it that we think might be better. Let me see. Okay, after analyzing the test results using pound fiber, we have come to the following conclusions. Controlling the nozzle pressures allows repetitive control of biomass location on the grate. Controlling the time lapse at a certain nozzle pressure allows repetitive control of biomass accumulation at a certain location. And changing nozzle pressures by steps provides a controlled bed thickness. Now, we are going to be exploring those very basic principles to see if we can improve biomass distribution as it is today. Boiler MAC, the definition of suspension boiler, includes the following sentence. The distributors inject air at the point where the fuel is introduced into the boiler in order to spread the fuel material over the boiler width. The combustion of the fuel material is completed on the grate or below floor, or the floor below. We see in many suspension boilers that in order to minimize the amount of biomass accumulated on the grate, a lot of excess air is introduced into the combustion. That generates a lot of carryover, and we can see that at the end, when we clean the gases and collect the biomass that is carried over, lots of biomass, I don't know if there you go, lots of biomass is actually not burned at all. I don't know if the people present have seen this in the boilers, but this means losing a lot of energy and obviously using a lot of equipment to clean up what you should have burned completely in the furnace. Boiler MAC has a new definition of a boiler called hybrid suspension grate boiler with subtle differences with regards to the suspension boiler. It says with air distributors to spread the fuel material over the entire width and depth of the boiler combustion zone. And the combustion is completed on the grate or floor of the boiler. Now, the importance of a thin bed on the grate is due to the fact that if you provide a controlled thickness of bed that burns between 1 and 3 inches deep over the complete area of the grate, this assures a continuously burning grate bed which rapidly dries and heats the biomass, fibers, and suspension. This is critical. You're not just throwing a lot of air trying to keep everything off the grate. You are generating a very uniform heat transfer per square footage or per unit area of the grate. And that in itself is the key to stabilizing combustion. We will see that in a minute. When the fuel bed is partially uncovered, or when it is very thin, less than 1 inch, the ignition zone immediately above contains an unstable and highly fluctuating flame, which has been seen and recorded by some researchers. Of low luminosity, meaning it provides low radiant heat for the heat transfer, that induces combustion cycling, which becomes evident with furnace puffing or cycle pressurization. When the biomass accumulates in piles above 6 inches, it reduces the grate heat release, meaning that what you calculated as the average heat release is not going to happen. It also creates combustion cycling and high CO exiting the furnace. That shows I'm nervous. Conclusion. Optimizing biomass distribution on the grate while burning the rest in suspension with minimum excess air is ideal for stable combustion and efficient steam generation. Now, we were told that we should show this, but unless you clean the gases and you are not doing a good job at distributing the mass over the grate or having an efficient combustion, this is what we get, and we have worked a lot in hiding incomplete combustion. We have developed many things to hide what happens, and obviously there is a cost to that, both in maintenance as well as in power generation. Dr. Terry Dixon is an Australian who has done a lot of work throughout the years, over 30 years, studying biomass combustion. There are a couple of articles here that we leave for you to take a look at. He's co-author of a patent on the system that we call the spread-on grate. The true hybrid suspension grate boiler. I contacted someone at Boilermat trying to understand what was the idea of the new definition of hybrid suspension boiler, and I didn't quite understand the response. But what we think that is meant by covering the width and the depth is being able to control it, and we think that in order to do that, there are some essential concepts to maintain. The biomass will be thrown into the furnace depending on the air pressure behind the nozzle as well as the efficiency of the nozzle. Nozzles used today, we believe, have been designed more to cut cost, to minimize the cost of them, than to optimize the aerodynamics of their work. In other words, the idea is to place the air and put some air so the fuel is dumped or thrown or pushed, rather than truly position it somewhere. The control variables are PS, we can see a little graph here of time of a cycle, and we call the cycle in the automated system is the time between startup at a certain pressure and then step by step lower it down to final value of that cycle, and then going back and repeating it over and over. And you can, by controlling these three variables, control the position of the whole biomass over the whole grate. PS is the step pressure, TS is the cycle step time, and TCH is the change, the cycle step change time. Time it takes to go from one pressure to the other. And by controlling these three variables, you can actually position the biomass, even though it varies in density or moisture, throughout the depth. And when you spray it open well enough, it also spreads wider, and therefore, as you have various feeders, you can control the biomass coverage of the whole grate. The typical biomass spreading system is this system. It uses a butterfly valve that is rotating continuously. They can change usually the frequency or the RPM, and it discharges into a nozzle, and that nozzle basically creates what we will see in a minute, a continuous back and forth cycle that really does not provide any predefined control, and it cannot be changed. Once you have the butterfly turning, you get what we're going to see in a second. These are some pictures of current or existing types of distributors. The video on the right is showing two gauges. The one on the right is what you see today. If you take a pressure gauge and connect it to the box that actually sends the air behind the nozzles, in any one of the existing distributors in the market, as far as we've seen them, you will see that it continuously goes back and forth. It does not either step up or down, or stay at one point in particular. So the graph here is what you get. Now, typical biomass spreading does not do this anymore, but if you want to eliminate both worrying about what happens at the grate, you don't send someone to go and move the biomass, but something is doing it, whether it is steam nozzles or the grate has the hydraulic steps that move back and forth. But you are trying to handle a problem which was not handled properly to begin with. Oops. Now, in places where you do not have all the cleaning equipment, it is very easy to see this type of thing. But the important thing is that that happens today in all the boilers that cannot control the accumulation of biomass on the grate. There is a very interesting patent, recent patent, that says the following within the patent. Attempts to more evenly distribute the fuel on the stoker have employed rotating valve dampers to vary the air pressure. The use of such rotating valve dampers has led to fuel being distributed more evenly, but has resulted in the tendency of the fuel to collect toward the rear of the stoker, and thus has not effectively solved the problem of inefficient combustion. Now, this is the state of the art. These are the people who have the state-of-the-art distribution of biomass within landfills. We decided to build a test site where we are using our automated valve injection system. We call it spread grate. But we are using it to see how the biomass responds to various pressures if you actually provide a good, effective momentum to place the biomass. And this has given us interesting results. We can adjust the pressure between 1 inch and 25 inches in steps as close to half an inch between steps. So if you connect this to a DCS, you have total and complete control of where at each second you are throwing the biomass onto a grate. So this is an electronumetric valve that we are proposing as the means to achieve this. It's run through the DCS control and the already prepared programs for that biomass and that grate. And these are the equipment required to throw it and do the testing. The testing is done in a room where you throw this and you place boxes that you can later on weigh and see where the biomass accumulated depending on the pressure that you apply behind the specific size nozzle. So by changing the nozzle dimensions and changing the pressure, you can provide throwing distances that have until now thought as impossible to achieve, 20, 30, 40 feet and beyond. So these are the tests, and if we take this data and we look at what it does, you basically come at distance, the throw distance, with the weight that is accumulated. You can correlate that data and finally come to conclusions like this. Between these two graphs, a change between 2 and 4 inches in water column, nominal, meaning between two highest points, you get 1 meter or 3 feet longer throw than you did before. And that kind of correlation done for any biomass with any moisture allows to do the programs to then assure that you can do it in any grade. The current design takes pressures from ducts and puts the air through this passage that creates not only high pressure losses, but also creates turbulence before the jet, and therefore you can require as much as 2 times the pressure with this type of valve than you require with this type of system. And what we are showing at booth 501 is a small version of this type of device. It's a venturi or needle valve that it approaches a seat that is shaped so as to provide closed control. You can have 30 inches behind it and obtain 1 inch out, or go from 1 inch to 30 inches of water by displacing it by 1 millimeter, 2, 3, 4, 5, and so on. Okay, so this is a valve that has, in terms of efficiency of recovery, a very high recovery rate. Now, the design that we have used in one sugar mill and in a few palm fiber mills is this design. This is the element that provides the control. It's a dynamically shaped plug, and the air can either flow from one of the sides or the whole valve can be installed into a duct. You can see the design here. We have developed control boards, small boxes, where an operator can select various programs depending on what he sees. So by just turning the selector, he can change completely the program that he's using to locate his biomass. Installation, this is a typical installation in a gas boiler, a 350,000 pound per hour. That's a palm fiber boiler. This is the type of control box that we were talking about. You can obtain a 50% reduction in the biomass lost through carryovers. You can obtain 10% or greater reduction in excess air, because when the typical operator increases excess air as soon as he sees that he has some problems with distribution of the biomass. And the unburned carryover and definitely increased combustion stability. Operators in control room reported over 15% decrease in biomass feeder RPM. Thank you for your attention, and we're ready to answer any questions you might have at booth 501.